Okay, ANOVA. ANOVA stands for Analysis of Variance. That's contracted form. That's ANOVA. It was invented in 1935 by Ronald Fisher. To me, it was really a very important invention. You should think that ANOVA is used on about 95% of scientific papers. So perhaps it is the most used technique. And it is the first and very basic technique, which is the starting point for everything. So it's rather important that you know about it, if you still don't know. Let's start from an experiment, which is really very similar to the one we did last week, where we had 3 genotypes to compare. In that case, we decided to take the first 2 and compare, then we compared the second with the third, and then the first with the third. Okay, so you see that this is not really very rational. We need a technique to decide whether there is at least one genotype or one treatment that is different from the others. Okay, so a sort of an omnibus test. And this technique is the ANOVA. So the experiment we are going to talk about now is, it is a real experiment I did maybe something like 25 years ago, or I don't know. It is a small experiment, but it's nice to make some hand calculations. Hand calculations. We will never do our ANOVAs by hand. I did at my time, because I didn't have the computer. Yes, and it is important to be able to do the calculations by hand to see what is this under the hood, what is behind. Otherwise, we cannot fully grasp the technique. Then we can do our calculations by using the computer, but at the beginning, it is important to do the calculation once by hand to see what happens. So here we have a small plot experiment with a completely randomized design. If you remember, with a completely randomized design, the treatments are allocated totally at random to the experimental units. In this case, we had pots that were the experimental units, and these pots were sown with a weed plant, that is Solanum nigrum. It doesn't matter, it is a plant, and we want to kill it. That is our job. So we wanted to compare 4 herbicides to kill the weed. And we designed the experiment with 4 replicates. That means 4 treatments by 4 replicates. It is 16 pots, 16 units. And they were, and the herbicides were allocated totally at random. So I hope the problem is clear. We sprayed at random, and we harvested the biomass in each pot and weighed it. So the response is the weight in grams per pot. So we have 16 values of weight in grams per pot. Of course, the lowest the weight, the highest the efficacy.
Highest what?
Yeah, because if the herbicide is very effective, then the plant doesn't grow. So it stays small and it weighs less. So the higher the efficacy, the lower the weight. The other way around. Okay? The lower the weight, the higher the efficacy. I mean, we look at the weight and decide about the efficacy.
Opposite relation?
Pardon?
Opposite relation?
Yeah, that's right. Because if the herbicide is very effective, then the plant stops growing and the weight is small. Right? And these are the results. So you see the table is really very similar to the table we were dealing with yesterday in our exercise. We have 4 treatments. In this case, you see we have 2 herbicides, rimsulfuron and metribuzin. They are used alone and they are also used in mixture. We wanted to see whether the mixture was more effective than the herbicides used alone. Okay. And then we added the untreated control. That is unweeded. There was no treatment. Okay. That is important because it shows us how is the development of untreated plants. So the herbicide is expected to reduce the development compared to the untreated plants. Right? So these are the data. 16 data. Now, first of all, I think we should load the data into R. Okay? So I'll show you the coding. I already written it because I wanted to make sure that the data set was at its right place. So we do like this. Okay? First of all, we clean everything. Then we set file name. Oops, sorry. Still making mistakes with this keyboard. I lost it. Never mind. So this is an internet address. So HTTPS colon / www Casa Onofri, that is my name, .it / datasets / mixture.csv. So let me check whether this works. Then we get the file name and use it inside the function read CSV, as we did last time, a few weeks ago. Then header equal true. That is not strictly necessary, but it says that the first line of our data set is made by the names of the columns. So let's see whether it works. So you see that we have 2 variables here. One variable represents the treatment with which each subject was treated. And the other variable, the other column, is the weight which we have recorded. So we need to work on the weight variable. So what we could do here, for example, describe descriptive stats for weight. So this is something you should be able to do by now. Are you okay, Ali? I didn't ask you.
First of all, it was okay, but now I didn't manage to do so. I'm searching if I got something wrong here.
Just give me 1 second. The Mac, which is giving you troubles. Okay. Right? You need a parenthesis here. You got 1, 2, open in brackets, just 1 close. Now you need to use, with Mac you need to use Shift, Command and Victory. Okay. And I think you need to use this one here. Not sure.
Which one?
No, the other one is okay as well. So common and return. The alternative does not work. Control and return or control R. They do not work with Mac. So the script starts for weight. First of all, we can calculate the mean for weight, and we call it mean. Okay. That is a bit confusing because me is usually reserved to the population. But we could see this as an estimate for the population here, because our interest is in the background for the population. So the mean of weight. Now you see that if I do like this, it doesn't work, because the vector weight is not in the workspace. It is inside a data frame. So what I should write is dataset $weight to tell R that the weight vector is inside the dataset data frame. Right? So I get me. E is 14.5 approximately. Then I want to calculate the standard deviation. But first we calculate the deviance, and then we stop there. I want to call this total deviance, and I'll tell you why in a few seconds. Total deviance, tot dev, that is equal to the sum of squared residuals. That is, we take data sets and weight, subtract the mean, and square. That is the deviance, you remember. So I take every value, subtract the mean, and square. And then finally we sum the squares. So you see that I have nested two functions. The first function is, so they are three indeed, because the first function is to take weight and subtract mu. You see, mu is just one value. There, in dataset weight, we have 16 values, but mu is recycled, as I said yesterday. So it is subtracted from all values in weight. Then, see that there are brackets here, and the result is squared. You see here. And then we sum all the squares. So we get the total deviance. Is equal to 1263.7. Okay, so this is what we need now. We could go ahead and calculate the variance and the standard deviation, but we will not do it now. So far we need this. We need to know the mean, the overall mean, and we need to know the total deviance. So we will not look at this slide here, because this is what we did yesterday. So we made a description of the groups, of the treatment groups. We could do this, but we will not do it now because it's not necessary now. We did it yesterday. What we have to look is this. This is important because we go back to our modeling side. So we want to write a model now where the response, y, in this case it would be the yield, or the weight, sorry. The weight is expressed as a function of three values. Okay. One value is the overall mean, and we know that already. The other value is the treatment effect. What do I mean? If we go back to this slide here, we see that the means are different for the different treatments. So there must be a treatment effect somewhere. This treatment effect takes the value and moves it away from the overall mean. So we have the overall mean, and then, for example, with metribuzin, the overall mean was 14.5 roughly. So with metribuzin, the mean is lower than the overall mean. That means that the treatment effect is negative. With the mixture is even more negative. The herbicide decreases the weight with respect to the overall mean. With rimsulfuron, the effect would be positive because the herbicide increases the weight with respect to the overall mean, and with the unweeded, of course, it is even more positive because the weight is much higher than the overall mean. So this would be called the treatment effect. So what is the treatment effect? We have the overall mean. The treatment effect is what moves the observed value away from the overall mean. And it represents, right, the treatment effect. Okay? So, if we stop here, then it's not enough, because as we have 4 treatments, if the model would stop here, we would only have equal values for the units which were treated the same way. Okay, because they have the same treatment effect as the treatment is the same. Okay, we have replicates, you remember, we have 4 replicates, and the 4 replicates should have the same value. That's why we include the third element, that is epsilon, and it is the random stochastic effect, which is individual. So every observation has its own random component. Okay, so we have basically 2 effects acting on the overall mean: the treatment effect and the random effect. Everything else but the treatment. So, is this passage clear? I mean, we should wonder why the observations are one different from the other. They are different because there are 2 effects. One effect is the treatment effect. Of course, they are different because we treated them differently. Then there are other effects which we do not know. They belong to chance. Okay, these effects are possible. Maybe the weight, the pots were not equal. Maybe the amount of soil inside the pot was not equal. Maybe the seeds were not equal, and they certainly were not equal. There is individual variability, so some seeds were more resistant than others to the treatment. Okay, some seeds were more quickly growing at the beginning. Some seeds were slower. There is variability, and you need to consider that this is a weed. It's not a plant, a crop plant. So weeds are natural plants, and they are not hybrids. So they are not homogeneous in terms of genetics.
So why is it carbon?
Yeah.
This issue around that component, is it known issue or is it?
I think I should say that just a random component. Okay, so what we do not know, what we are not able to know, we put everything inside this component. That's the random component. So if we have made a good experiment, meaning all the units are alike, very homogeneous, we have operated well, we have done a good treatment, the dosage was exactly estimated, and everything else. If we have done a good experiment, the component epsilon should be small as possible. But if we have not done a good experiment, epsilon is big. And the treatment effect pertains to alpha. And you see, we are trying to part the two effects. The deterministic effect of the herbicide, the effect we are studying by doing this experiment, and the stochastic effect, everything but the treatment, which should go inside the final component epsilon. Okay? And then as we said, we cannot model epsilon because it's random. Therefore, we just make the assumption that it is normally distributed with mean equal 0 and a certain standard deviation sigma. Sigma is the standard deviation for the error effects. Okay, so what we need to do now is to try to estimate the parameters of this model. We will have one common intercept, μ, that is the same for all observations. We will have 4 alpha values because we have 4 treatments, and we will have 16 different epsilon values. That's a stochastic component that is different for every individual because it is totally random. Okay? So you see, you need to note this. What we are doing now makes 4 assumptions which we need to consider. First, we have a model, deterministic, which is purely additive because we are adding mu to alpha. So it's purely additive. There are no other effects apart from the treatment and random noise. This is an assumption. There are no components of systematic errors. Okay, this is a very important assumption. There is nothing we can do about this apart from doing a good randomization. It is the randomization process which ensures us that there are no systematic components of errors. So we are linking to the experimental design now. Because if the design was not done properly, this second assumption would not be valid. Okay, so it's important that we design the experiments properly and we avoid systematic errors, otherwise our analyses are not valid. Okay, because we are talking about 16 independent errors, and these independent errors are sampled from a Gaussian distribution, so overall their mean should be 0. If we have a systematic component of error, if you remember, a systematic component of error tends to represent always with the same value and the same sign. For example, if our balance is not functioning properly, For example, because it adds 20 kilos to each weight, 20 kilos, 20 grams, whatever you want. Of course, we have errors that tend to repeat with the same value and the same sign. And that would be a systematic component. And we cannot describe it because our errors need to be sampled from a Gaussian distribution. Okay, so that's important. Then third, errors are independently sampled from a Gaussian distribution. So the observations need to be independent. You remember the experimental design. So we are really assuming that the experiment was done properly. Then fourth, this is more statistical, error variances are homogeneous and independent from the experimental treatment. So errors are just occurring by chance. And you see, if you look here, we only have one sigma value, which is constant for all observations, independent from the group or the herbicide with which they were treated. If these assumptions do not hold, then the analysis is invalid. Okay, so we need to be careful to these assumptions. We will talk about these assumptions next week. Now, it is important that you note that underneath there are some assumptions which we should make sure are respected. Okay? Let's go to parameter estimation. We will do here. So the model, I'm writing the model here so that we remember what we are talking about. The model is y equal mu plus alpha j plus I. By using j, because we have j treatment, j goes from 1 to 4. So we have alpha 1, alpha 2, alpha 3, and alpha 4. And we have 16 values of epsilon, right? So we know about mu. Mu is 14.5. Okay. Now we need to calculate alpha. To calculate, because we can calculate first the mu for the groups. Means for the groups. As we did yesterday. So we use the function supply. So we want to calculate, we want to work with weight. We want to use the treatment as the index, and we want to calculate the mean for the groups. Pardon?
Mean of data rate and data.
Yeah, these are the means for the groups, for the herbicides, and we will look at those. Okay. So you see, they totally correspond with the ones we saw before in the slide. So these are the means. Okay? Then we can calculate the alpha, because alpha is simply represented by the group means minus the overall mean. Groups, sorry, you see that I'm doing mistakes now and then, so it's perfectly normal that we do mistakes when we write our coding. Don't get frustrated because you make mistakes. It happens to everybody. The main thing is to watch carefully to what we write, because 90% of times mistakes are relating to small errors with capital letters or small letters, or just forgetting characters or other types of any nature. So here we go. This is alpha. What do we mean? And you see that the effect of treatments is measured considering how the overall mean is moved depending on the treatment. You see that the overall mean with metribuzin is decreased by 5.3 units. With the mixture is decreased by 9.4 units. So we are 9.4 units below the overall mean. So the treatment effect is negative, and that's positive for us, because it means that the herbicide is more effective. With rimsulfuron is not very effective because the plants treated with rimsulfuron weight more than average. And of course, the untreated plants, they weight much more than average. So we have quantified the treatment effects, right? So it's 9.31. What I propose is that we take a coffee now. Ali is not taking a coffee, but Wahel is taking a coffee. We take a coffee, but it's my turn to pay. No, because last time it was your turn. So I'm back, as you probably noticed, after the coffee. So we conclude this lesson and see whether we can reach the end. I hope so. Let's try to see what's happening now. We have the overall mean. Then we have the mean. We have calculated the means for groups. And then we have calculated the effects of treatment. Right? Now what I want to do is to develop the model by assigning to each individual its own parameters. Okay, so I'm building a table now. In order to build the table, I need to take alpha, and I need to look at the data set, and I see that in the data set, the subjects are divided by treatment. So the first 4 subjects belong to the first treatment, so they have the first mean. Okay, so I'll add to the data set. I do like this. Look at me. I'm taking alpha, which contains the treatments, the means for treatments, and replicate four times. Did you get this? So look here in this new vector, which I still have to define. I have 4 times minus 5.3, which is the effect of the first treatment. Okay, so I'm putting this inside the data set in the column alpha. Okay, and I also want to put inside the data set and word for you. Let me use small letter here. So I want to create a new variable. Fitted means the effect of the deterministic part of the model. So what would it happen if we didn't have any error? If we didn't have any error, we should have a value that is equal to me, the overall mean, plus the effect of the treatment. Okay, so look at me. I'm using alpha that is inside the data frame, because in that case I have 16 values. Okay, so if we develop this one here, you see, and this is my final result. I have a data set now which was enhanced by adding two columns. One column represents the effect of the treatment, and one column represents the fitted values. I mean, the first observation without the effect of errors should have been 9.17, 9.18. And so the second, and so the third, and so the fourth. Okay? The fifth observation was treated with the mixture, and it was 6.14, but without the effect of errors, it should have been 5.13. I hope the reasoning is clear. You know, what we are assuming here is that without the effect of errors, the most likely value for an observation is equal to the mean of the group to which it belongs. Right? So this was Fisher's idea, and it is a very, very brilliant idea to me. So now we can calculate the residuals, epsilon. And I put it inside data set, and epsilon is equal to the observation data set and weight minus data set $fitted. Okay, so I want to show you once more the data set now. Now we have all elements. We have the observation here. We have the effect of the treatment, alpha. What does this mean? It means, okay, I have mu, that is the overall mean, which is 14.5. In this case, the treatment effect subtracts something from the overall mean. Okay? And this leads us to the fitted value. The fitted value is obtained by summing me with the treatment effect. So we are excluding any other random effect. What is the random effect? The random effect is written here. So we can read this. The first observation, it was 15.2. With no error, it should have been 9.18. But the error produced an effect which was equal to 6.0. And that error brought the observed level to 15.2. Is that clear? Yes. This is really interesting. I mean, we are partitioning the effect of the treatment from the effect of the error. We are separating the two effects. I can make another example. Look at the observation number 5. So we have observed 16.14. Okay? The treatment...
Prof,
Yeah.
Can you please explain that fitted epsilon part once, because it was not clear to me.
She said fitted. Did you say the fitted part?
Yes, fitted epsilon.
Yeah, I'll do that with this example. Look at the observation number 5. So what we observed was 6.14, right? That was the weight we measured, okay? So in this case, the treatment effect was -9. So that means that with respect to the overall mean, the treatment effect produced a decrease of weight equal to 9.35. Considering this effect, so perhaps I should do another thing, if you just to show you a little bit more properly. Adding this here. Okay, so I added mu at the end. So let's go back to the fifth observation. It was 6.14. The overall mean is 14.4. With respect to this overall mean, 14.5, there was a decrease equal to 9.35. This was due to the treatment.
Yeah.
So what do we expect? This is the fitted value. What would we expect without any random error term? We would expect that the observation number 5 should be equal to 14.5, that is the overall mean, minus 9.36, producing a value of 5.13. Okay, so if you add the overall mean and alpha, the treatment effect, you get to the fitted value. The fitted value is what we would expect without any random effect. But we see that the observation is different from the expectation. Why is it different? It is different because of random errors. And if we should quantify the random errors, we could compare the observation with the expectation. If I subtract the expectation from the observation, I get the error term, epsilon. Indeed, you see that we expected 5.13, and there was a positive error term equal to roughly 1, which brought the observation, the observed weight, to 6.14. Is this clear? I want to do another example if you want. We can look at this observation here, number 9. Okay, so we observed 10.5. The weight was 10.5 grams per pot. Okay? What was our expectation? We look at the treatment effect. On average, the treatment effect moved the value with respect to the overall mean, that is here. It moved the value up by 2.4 units. So we mean that in pots treated with rimsulfuron, there were on average 2.4 grams more than the overall mean. So the treatment effect is 2.4. Okay, so if we consider the treatment effect, we should have obtained, our expectation is that we should have obtained 14.5 plus 2.4. That makes up 16.86. So this is our expectation with no random error. But we did not obtain a weight of 16.986. We obtained far less. Why did we obtain far less? Far less. We obtained far less because there was some random effects which we do not know anything about. We do not know anything about, but we can quantify it. It is equal to minus 6.4. So there was some random error term which brought the weight down by 6.4 units. That is our reasoning. What was the name? The name was No Sheen. Is this clear now?
I think Christina.
Yes.
Not Christina, yes.
Oh, okay, sorry. I just heard your voice without seeing who was speaking. Sorry, it is terrible to find in this situation because I don't see you. I just see Wahel and Ali now, and I don't see you. I hope you can come in presence soon. Otherwise, this is not teaching. Yeah, otherwise this is not teaching. It is something different. So, Christina, was it clearer now?
Yes.
Okay, thank you. So now we have all the pieces we need because we know alpha, we know epsilon, and we know mu. If we go back to our model, this position, this was the model here. Now we know everything for every individual observation. Okay? So, okay. So now we can really work a little bit on these elements here and do the so-called variance partitioning. Please remember, we started before from the total deviance, dot dev. We calculated it before. This was the total deviance. Oh, sorry. I have cancelled everything. I need to rerun all coding. Tot was
big T.
Oh, tot dev and tot dev. This is capital. Okay. Tot. Okay. So it expresses the variability of yield, the overall variability. So I'm just asking you, where does this variability come from?
Summation of the.
Okay, Ali is telling me summation of.
And they say that those errors
of treatment plus random effects. I mean, if the data are one different from the other, that depends either both from the treatment and from random effects. Here, this is the total deviance. I mean, we did not make any distinction before. We just compared the sum of squared residuals with respect to the overall mean. And if one observation is different from the overall mean, it depends on the treatment effect and on random effect. So this is the summation of everything, includes everything.
So now we are even dividing the main.
That's right. That is our job now. We want to split this component here that is equal to 1200. We want to split this component in two parts. One due to the treatment and one due to random term. And it is pretty easy because we could take alpha now, mean for alpha is obviously 0. See, it is not exactly 0 because R has got an approximation in very small values, and the smallest values it can represent is roughly 10 minus 16. So a negligible value. This is 0 indeed. So if the mean is 0, I can calculate would be the treat. Let me, instead of talking about deviance, let's talk about sum of squares. This would be the sum of squares for the treatment, SST. We get it just summing the squared alpha values. Because the mean is 0, so we don't need to subtract the mean. This is a deviance. We subtract the mean, but the mean is 0, so we don't need to subtract it. So we simply square and sum. And this is the sum of squares for the treatment, which is, you see, smaller than the total sum of squares. Of course, now we are considering only the treatment effect. Look at this. This value here, this alpha value here, only depend from the treatment. So this would be the treatment effect. And we can also calculate the deviance for the error term. How do we do? Where is the error here? It is not here because we did not add it.
We can
what can we do now?
making minus something.
Yeah, we can take that and epsilon is equal to data set weight data set and fitted. Right? Here we go. These are the errors. I think we added it there somewhere, but
It was added, but now
it's gone. I don't know why. Doesn't matter. We got it.
Yeah.
So now we take this. I'll show you this now. So now we have all elements here. This is the random element. And we can take that the mean for the random element is 0. Again, not really 0, but a negligible value. So again, we can calculate the sum of square by summing and squaring epsilon values. This would be the error effect. That's the overall error effect. And it's equal to 184. It's interesting to notice that if I sum treatment effect,
we will get the total.
just check it.
Okay.
Here we go. You see? So we see that we have partitioned the variability of the weight in two components. One component is due to the treatment effect, and the other component is due to the random effect.
So before we used to describe this error or the deviance in general, we didn't know whether it was from the experiment, the stochastic effect, or was the deterministic effect.
Yeah.
So now we are able to divide this error, this deviance, into two parts. The one that's related to the stochastic effect, that is the epsilon, And the other one is related to the final result. I can manage like the difference in the weight between one wheat and the other.
Yeah. So I think that Ali gave us an explanation. You could take my place, because your explanation was excellent.
Thanks.
So there was a variability. So this is what Ali said. I'm repeating because I'm not sure whether you could hear him from home. Ali said, at the beginning, we had the weight, and this vector showed the variability. So the data were one different from the other. And we did not know which effects this variability could be attributed to. Now we have managed to split the total deviance in two components. One is due to treatment effects, and it relates to alpha. And the other one is due to random effects, and it relates to epsilon. So now we know where the variability in weight comes from. A main part comes from the effect of the treatment, and it is quantified in SST 189.5. Okay. And another part, which is smaller, 184. So sorry, the other one was 1089. Maybe I said 100. I don't remember. So it was 1089.5. So a very big part. A small part, 184, came from errors, stochastic effects. Okay, so this is the analysis of variance in brief, partitioning the total variance in two components. One is due to treatment effects, deterministic effects, because the treatment was manipulated by ourselves during the experiment. So it's a deterministic effect. We imposed it.
Yes.
And the other one only relates to random effects. And that is the reason why the observations belonging to the same treatments are not equal to each other. Because if there were no random effects, we should observe the same weight for all the subjects, the pots, treated with the same herbicide. Right?
Yes. Can we infer something regarding if the SST was bigger? In this case, it is bigger than the SST.
Yeah.
But this should give us a hint for something later on, that in general, the effect of the materials used or the herbicides used contributes really to the decrease of the weight, and not in general the seeds, the stochastic one. So in this case, the materials that we are applying, the herbicides, are doing their job. And so it's affecting the herbs regardless to their genotype.
Well, I'm just stopping you because Ali has gone a bit too far away with his reasoning. Before we can infer, I mean, the idea was, please correct me if I'm wrong, Ali's idea was that we could compare the deviance for the error and the deviance for the treatment.
Yes.
Okay, so we can't.
Okay.
We can't, and you know why. I said that a few lessons ago. I said we cannot use the deviance to compare samples with a different number of degrees of freedom, because the deviance depends on the number of residuals we sum up. If we have a lot of residuals, then the deviance becomes high. And if we have a few residuals, then the deviance is small, even if the variability is high. Okay, so you might say we have 16 elements, either in alpha and in epsilon, so we should be able to compare. But I will tell you, no, we can't at all, because we need to consider the degrees of freedom. And let me show you again.
Even if we repeat the same experiment with 16 values, we will get 14 different SST and SST.
But that's not the problem with degrees of freedom. The problem with degrees of freedom is another one. Look at me. Look at alpha. The treatment effect, SST, is made up by summing and squaring the alpha values. How many of these values are free to move? Not 4.
4 minus 1, it's a 3.
Yeah, and Ali got it. We have only 3 values here which are free to move, because we have the first one, and it's okay, this is free. I mean, if we do another experiment, then the first residual is free to move.
Yeah.
But then the second, the third, and the fourth, they are not free, because they belong to the same treatment, so they need to be equal to the first one. Then the fifth one is again free. If we make another experiment, we will notice that this value has probably changed. But the other ones are not free because they need to be equal to the first one. So we have 2 degrees of freedom. And if we consider the third treatment, then we have another degree of freedom. And then if we consider the final treatment, this is not free, because the mean for alpha needs to be equal to 0. So the final value needs to be such that sum to the other ones, it gives us 0. So this is not free. Here we have a number of degrees of freedom that is equal to the number of treatment levels minus 1. So for if we want to calculate the variance for the treatment, we calculate mean square T is equal to the sum of the squares for the treatment divided by 3. Okay. And this would be the variance for the treatment effect. Now let's calculate the variance for the error term. Now it's interesting. How many degrees of freedom do we have here?
It's 16 minus 1. But for the error, each one alone.
No. It's not 16 minus 1. That is correct for the total deviance, because we have 16 observations and...
But we got 4 treatments here.
Here we have 4 treatments, and please consider that epsilon was calculated by subtracting from the observer data the mean for each treatment.
But the mean for each treatment is the same for the 4 characters, so we got 4 means only.
No, you have to think about this. Think about one mean. One mean is made of 4 treatments. So for one treatment, we have 3 degrees of freedom.
Okay, so 3.
So we have 3 degrees of freedom.
12.
Yeah, 4 treatments. So it's 12. 12. And look at me. It's really interesting here. Fisher was a genius, because if you sum up 12 degrees of freedom for the residual and 3 degrees of freedom for the treatment, you get 15, which is the total number of degrees of freedom.
Yes.
That's interesting, you know. So if we want to calculate the mean squared for the error term, we have to divide the sum of squared for the error term by 12. that is the product of 3 degrees of freedom per treatment by 4 treatments. Now we can compare. We can compare mean square for treatment. That is 363 with the sum of square for the error term. That is much smaller. And now we can compare. Okay? Now this is a very important passage. Okay. So we have partitioned the deviance in 2 parts. One is due to the treatment and one is due to the random term. These 2 deviances cannot be compared because the number of degrees of freedom is not the same. How many degrees of freedom do we have? Let's consider the treatment effect alpha. We have seen that we have just 3 degrees of freedom. In general, the number of degrees of freedom for the treatment is equal to the number of treatments minus 1. So we have 4 treatments, 3 degrees of freedom. The number of degrees of freedom for the error term is equal. We have to consider each group and the number of degrees of freedom in each group. In the first group, we have 4 individuals, and therefore we have 3 treatments, 3 degrees of freedom. So we have 3 degrees of freedom per group. We have 4 groups. The total number, the number of degrees of freedom for the error term is 4 by 3, that is 12. So we have partitioned the deviance and we have partitioned the number of degrees of freedom because we have 15 degrees of freedom in total and they are split into parts. 12 go to the error and 3 go to the treatment. Now we can calculate the variances and we can compare the variances. And Fisher said that we should compare variances by calculating the F. F stands for Fisher F ratio. Okay, that is a ratio between the variance of the treatment and the variance of the error term. It is 23.7, right?
Yeah.
Now, final move, and then we stop. And tomorrow we do exercises, and you will see that it is rather easy. Any questions so far?
I think it's clear.
Well, I don't believe it is totally clear because you have to go through and try to do it again. Okay. I just want to show you that we can do this the easy way. Instead of doing all the calculations, we can ask R, please do the calculations for us. And that's pretty simple. So, ANOVA with R, it is pretty easy. First we fit the model. Remember the model, I'm writing it again here. The model was y equal to the intercept plus the alpha effect plus the error effect. So coding a model would be pretty easy. We use the function LM, that stands for linear model. Then we have to tell it, what is the y variable, the response variable. The response variable is dataset dollar weight. Then we need the tilde, which is this character here. It's a problem for those who are on Windows because we don't have the tilde. Therefore, another possibility is to go to the internet. You open your Chrome or any other browser, internet browser, type tilde, and you get here the tilde, and you can, for example, go here and copy the tilde from here. That's one possibility. Once you got the tilde, you don't need to write the intercept because it's fitted by default. You just have to write the factor variables, dataset and treatment. This is our fitted model object now, and we can explore it with the ANOVA function, and this gives us exactly the variance partitioning we have done before by hand. Sorry, I didn't understand the first part of the question.
Are having the ability to do this?
Yes? Yes, sure. That's it.
No, why do we need to?
Why we need to do it by hand?
Yeah.
You don't? You need to do it by hand if you want to understand what is underneath. To me, it's okay if you are able to get this table from R. But I found that all students are puzzled by this table because they wonder, where do these values come from? And that's why I'm doing the hand calculations at the beginning. Because now we know where these values come from. Okay. For some of you, that's simply too much. And they are happy with the result. To me, you need to understand that we have taken the whole total deviance and we have partitioned it into parts, okay? And these two parts are written here. One part, the second part. If you sum these two parts, you get the total deviance. And as well, the degrees of freedom have been partitioned into parts. You have 15 degrees of freedom in all. They were partitioned in 3 and 12, which are attributable to the treatment and error. Then from these deviances here, we calculated the related variances. These are here. And then we calculated the F ratio. That is the ratio between the mean square for treatment and the mean square for the error. Now we need to interpret the p-value, but we will do it tomorrow. The partitioning is over. Fisher brought us here. Then Snedeker brought us to the formal hypothesis testing, but we will do this tomorrow. So far, what we can say is that the variability produced by the treatment was 23.7 times higher than the variability produced by the error effects. This is important because it let us think that the treatment effect is probably significant. But we need to take a decision by a formal hypothesis testing tomorrow. Okay, but it is, you know, a hint that the treatment effect is possibly significant. Okay? So it's 10:30.
Yeah.
Any questions here?
Time runs.
Time runs. And that's complex. But now we need to do some practice. And we will only talk about ANOVA models for a couple of weeks now. So you will be able to practice with this kind of models, variance partitioning. We will do the partitioning for more complex models, but the technique is always the same. And we will never do, we will no longer do hand calculations now. Because I just wanted to show what's behind. Now, the way to do a partitioning is this one. Fit a model and use the ANOVA function. Okay? So, see you tomorrow then. I'm saving this. I don't think you need that because it's already available here in the presentation, which you have at your disposal. And of course, chapter 7 is also at your disposal. It's already online. Now I have to check whether it is in Unistudium as well. So, see you tomorrow then.